Hello, my name's Fred Davis. I'm a Peter Buck postdoctoral fellow in the Department of Mineral Sciences. I'm an igneous petrologist, which means that I study magmas and igneous rocks, which form as magmas cool and crystallize. So some magmas are erupted at the surface as lavas from volcanoes, like Kilauea in Hawaii, which is pictured here, which is actively erupting today. So volcanoes are found in many places in the world, but their distribution is not random. You can see that there are many volcanoes encircling the Pacific Ocean in a region that's commonly referred to as the Ring of Fire. These arc volcanoes exist here because it's a place where old ancient oceanic crust is being returned back into the deep earth. And this is a process that drives volcanism. Perhaps less familiar to you are mid-ocean ridge systems, shown here in brown, that occur deep in ocean basins. And these are places where tectonic plates are moving apart, and they form long linear chains along the axis of motion that are volcanoes that are erupting basaltic lavas and forming new crust. So volcanoes occur in places where new tectonic plates are being created and where old tectonic plates are being destroyed. But there are also some volcanoes that occur in the centers of tectonic plates far away from tectonic boundaries that have nothing to do with plate tectonics at all. I've circled 3 famous examples here, but there are dozens more. Hawaii, for example, Iceland, and Yellowstone. And we refer to these types of volcanoes as hotspot volcanoes. And what's happening here is that deep within the earth, there's a thermal anomaly. The rock is really hot and buoyant. It rises towards the surface and begins to melt, and the magmas that form chains of volcanoes. And these volcanoes provide a really interesting avenue for us to explore the chemistry of the inside of the earth. And so let's take a look at a cross-section of the interior of the earth. You can see here in gray at the very center is Earth's iron metal core. At the surface is a very thin layer of rock called the crust, which we're all familiar with. But the largest layer of the earth, shown here in pink, is Earth's mantle. And the mantle is made of solid rock, but it's very hot, and it's under pressure, and it flows on geologic timescales. And magmas that form volcanoes form at the very top of the mantle. So if we want to learn about how volcanoes form, we have to understand the physics and the chemistry of Earth's mantle. But the mantle's deep enough that we can't actually drill down and sample it directly. Fortunately, volcanoes sometimes bring samples of the mantle up to the surface where we can go and pick them up. So what I'm showing here is a boulder of basalt. That's this black rock here, which is a volcanic rock. And this basalt has erupted with these small green rocks in it, and these are rocks that came from Earth's mantle. Here's a closer look at one. This is a mantle rock from Hawaii. This rock is called peridotite, and it's the most common rock we find in Earth's mantle. And probably its most distinguishing characteristic is its green color, which it gets from this mineral, olivine, which many of you may have heard of before as the gemstone peridot, which is the August birthstone. Olivine is the most common mineral in peridotite, which is the most common rock in Earth's mantle. But a question that drives my research is, are there other rocks in the mantle as well? This image is a cartoon showing a cross-section of the Earth. So what we're looking at the top, right, is a blue layer that represents the oceans, and then beneath that, a dark layer that represents the basaltic ocean crust. You can see in red here the mid-ocean ridge where new crust is formed, and on your left, an arc volcano showing where ancient crust is returned back into the mantle. And what this cartoon is trying to depict is what happens to that crust after it returns to the deep earth. It mixes back in, and the question is, does it remain as a separate type of rock that might be sampled at a volcano sometime much later in geologic time? And so the questions that are important to my research are, what happens to crust when it's returned to the mantle? Is it just remixed back into the mantle and dissipate back into the peridotite rock, or does it remain a separate type of rock in the mantle? And if so, what's the distribution of those rocks in the deep earth? Okay, so I try to answer questions like this using the chemistry of rocks from the mantle. And one tool that I can use to learn about rock chemistry is the electron microprobe, which we have one housed here in the Department of Mineral Sciences. And the way that this instrument works is that it fires a beam of electrons at my rock sample. Those electrons bounce around and interact with the atoms in the rock, and they release X-rays, which we can measure, and then learn about the chemistry of the rocks. So let me show you an example of something that I've learned. So if I take a look at rocks from Hawaii, mantle rocks from Hawaii, and look at the mineral olivine in them, I can look here on the x-axis at the magnesium to magnesium plus iron ratio, and on the y-axis at the iron to manganese ratio, these olivines. And what we see is that the chemistry of peridotite rocks from Earth's mantle in Hawaii form two different populations. One that's representative of normal background peridotite mantle, and another set that show the signature of recycled oceanic crust. And so what this is telling us is that in fact our Earth probably does look something like this cartoon. It's a mixture of different types of rocks that have been created through stirring over geologic time. And it's probably best described by a term that was first coined by French geologist Claude Alleg as a marble cake mantle. And so I'm very excited to get a chance to share with you guys what I'm learning about Earth's mantle and the different flavors of rock that we find there. Thank you.
Are there any other kind of xenoliths that come up? I've been to Hawaii and seen the green ones, but I'm just curious if there's any other ones.
Yes, absolutely. Peridotite is not the only type of xenolith. The xenolith is a rock from the mantle. I don't think I actually used that term in the talk. And there are other types of rocks as well. We see things called pyroxenites, which are closely related to basalts. And their origin is sometimes disputed whether these represent recycled crust or if they're in fact cumulates, which are minerals that have settled out of a magma during the formation of the magmas at the volcanoes where the xenoliths are erupting. Thanks, good question.
Fred, can you, over here, say a little bit about how you're planning to use the collections that the Smithsonian has to enhance your work?
Sure. So the xenolith that I showed from Hawaii is actually a rock that's from the National Rock and Ore Collection. Some of the work I've done here is looking at xenoliths from Hawaii to learn more about the mantle there. We have an enormous collection of xenoliths from Hawaii here at the museum, and that's been exciting to get into the drawers and find what we have there. So I have been using the collection in my work already, and I'm excited to learn more.
Fred, you showed beautiful pictures of rocks erupted to the surface in Hawaii from some volcanoes. But why do the famous big volcanoes, Mauna Loa and Kilauea, erupt no such rocks?
Thanks for the question, Dick. The reason I think that we don't see xenoliths in the larger tholiitic volcanoes is probably because they were there at some point in the history of those volcanoes, but because those rocks are undersaturated in olivine, they probably dissolved those xenoliths away long before they ever erupted at the surface.
I'm going to try to make a connection between the two of the talks. This is a question for Fred about why there might be more arsenic in the Andes. Is there a plate tectonic reason for that?
Is there a plate tectonic reason why there might be more arsenic in the Andes? I'm hearing from the audience that the answer is yes, but I'm not sure how I would. I'm not sure I have a good answer for that question.
Yes, I'll say that, it's an arsenic-rich region, and I don't know if I could say offhand why the arsenic is there, but the exposure is occurring because the water is actually coming from the plateau, from the mountainous regions, and that's the problem today, and probably would have been in the past, that even the people in the Atacama Desert, that the water is coming from actually an arsenic source.
Okay, I do have an answer to this question. The reason is probably because there have been in the past arc volcanoes there, and one of the things that volcanoes tend to do, right, is that they concentrate interesting trace elements. And so what happens, right, is that I've been talking about basalts in my talk, right, and these are magmas that are derived from the mantle, but the rock in the mantle is peridotite. It's a different kind of rock. And so things that tend to go into melts get concentrated where you have volcanoes, and arsenic is something that would rather be in a melt or in a fluid than in a solid rock, and so it gets concentrated places where there are volcanoes.